Hi everyone, welcome to this video. Now this one we're going to have a look at inverse relations and functions. Okay, so let's start off with saying A is the function or the set of points minus 1, 4, 0, 3, 1, 5. And we can say that the relation A is formed by mapping the following. So we've got minus 1, 0, and 1. Okay, well minus 1 is mapped onto the relation at 4. 0 goes to 3, and 1 goes to 5. Okay, so what we've done is essentially we've got some function or relation f of x. Now it might be, for the first one, could be plus 5, x plus 5. And it suits for all values. It's not going to be x plus 5 because the second one won't work. So just imagine it's x plus 5. So what we're saying is minus 1. It'll be f of minus 1. Well, that gives me minus 1 plus 5, so that's 4. For 0, it would be 0 plus 5. In this case, we've got 3. That's because this function is different to what it is. Okay, so the important part is we've got some numbers for x. It maps onto the relation at the corresponding points of y. So the inverse relation is formed by undoing the mapping. Okay, so that's going backwards almost. So we're saying we start at 4, 3, and 5. And so the inverse, 4 goes to minus 1, 3 goes to 0, and 5 goes to 1. So we're starting with these values and go to these values. Okay, so essentially what we've got is, okay, a point in our relation. We'll just look at the first one, so minus 1, and that's in our domain. And then that gets mapped onto this point over here inside the range. Okay, so it goes across. So that's what we do when we put in f of x or p of x or whatever it is. Now the inverse is by undoing that. So we're starting here and we're going backwards to that same point. So what we call that is f, and it's minus 1 of x. It's kind of like the inverse of sine and cos and tan, how we have that negative 1 up there. What's the inverse of it? So we're starting with this point, and we get the original point that we started with. So we can say the inverse of A is going to be 4, minus 1, 3, 0, and 5, 1. So we've basically just swapped them around almost. So the x and y coordinates of the point in relation A have been interchanged in its inverse. So this causes the domains and range to be interchanged as well. So as I shown, okay, the domain of A could be those points. It's equal to the range of its inverse. And the range of A, these 3 points, is going to be the domain of its inverse. And we get a bit of a summary here. So for any relation, the inverse is obtained by interchanging x and y coordinates of the ordered pairs. Domains and ranges are interchanged between pair of inverse relation. Alright, so the equation of an inverse. The effect of the operation, okay, multiplied by 2. Okay, so let's say we're going 2x equals 4. Alright, and we're solving for x. Well, what we're doing is we're doing the inverse operation. So 2 times x, the opposite of multiplying by 2 is dividing by 2. Okay, or we can multiply it by its inverse, which is half. 2 different ways you can do it, and it gets the same answer, equals 2. Okay, so the inverse operation is either of those two bits. And same thing with subtracting and addition. So if we subtract 2, we do the inverse operation, and that's adding 2, and so on. So these are examples of inverse operations, and we can use these undoing operations to solve equations. So, algebraically, interchanging x and y in the equation y equals 2x. So, we've got y equals 2x. Well, what happens if we interchange the x and the y? So, the x goes where the y is, and the y goes where the x is. So, x equals 2 times y. Okay, y equals 2x gives x equals 2y. Now we need to make y the subject. So at the moment we started with a relation, y equals 2x. We swapped the x and y. Now we just need to rearrange this y, or this equation, so that we have y by itself. So instead of x equals something, we need y equals something again. So that's just by dividing by 2 to get rid of that 2. Oops, x over 2 equals y. Okay, dividing by 2, 2's cancel, divide by 2. And that gives us the inverse. So y equals x on 2, that's the equation of its inverse. How do we obtain the equation of the inverse? Well, we just do exactly what we've just done. We interchange x and y in the equation of the original relation or function and rearrange to make x the subject. I think it should say y as the subject, so it should be y equals something. So as we did here, y equals 2x, we interchange them, and then we make y equals something x. So that's the inverse, and that's all we do. So let's go into a quick little example. I'm just going to make one up. So let's say we've got the relation y equals, we'll go 3, y equals 3x, something simple. And we want to find the inverse. Inverse, yep. Anyway, pause the video here, have a go. What do you think the inverse of that is? Okay, so interchange x and y. So we'll have x equals 3y. And now I just need to make y the subject, so dividing by 3. So we should get y equals 1/3 x, or x over 3. Alright, pretty straightforward. Now, next one, something a bit more complicated. Let's go y equals 2x take 8. Alright, find the inverse. Pause the video and have a go. Okay, so first step is interchange x and y. So x equals 2, y take 8. Next step is rearrange so we get y the subject. So plus 8 and then divide by 2. And that's the inverse. So that's all we do, is just swap the x's and the y's and then rearrange so we get y equals something in terms of x. Now let's go back up a bit. Alright, so in some cases the domain will need to be included when stating the equation of the inverse. For example, to find the equation of the inverse of y equals the square root of x. So let's have a look at that. Y equals the square root of x. Interchanging the coordinates. So finding the inverse, we'll get x equals square root of y. Expressing x equals square root of y, so we have y as a subject, we get y equals x squared. Okay, so that's just solving, so we get y by itself. Squaring both sides, we'll have y equals x squared. Alright, so what we've just been doing is just interchange x and y, make y the subject. Now this rule is not unexpected, since square root and squaring are inverse operations. Okay. However, as the range of the function of y equals square root of x is 0 to infinity, this must be the domain of its inverse. Okay, just looking at this one here. So y equals the square root of x. This is what it looks like. Okay, roughly. What's its range? So its range is all these values here. So from 0 to infinity. Okay, goes up to infinity. Now, what this is saying is, since the range of the function is 0 to infinity, this must therefore be the domain of its inverse. Okay, so the range becomes the domain for this. Hence the equation of the inverse, y equals square root of x, is y equals x squared, with the restriction that x has to be greater than 0, or 0 to infinity. Okay, so that's what we're saying here. So our inverse is y equals x squared. We have a range from 0 to infinity, and when we do the inverse, for this one our range is from 0 to infinity, and then when we find the inverse, it's going to be our domain for the inverse function. So how does that work? Well, let's have a look. I'm going to draw let's go a red line. Alright, I'm going to draw a line up the middle of our graph. Now, we've already got our original function that looks like there, and we know our range is from 0 to infinity, and as with our domain, goes from 0 to infinity. But just looking at the range. Now, what did we do to find our inverse? First step, we interchanged x and y. So every x point on here now becomes the y point on our inverse function. So what I'm going to do is, let's say, okay, that point there, don't know what it is, could be 1, 1 or something like that. Actually, it won't be 1, 1. Don't know what it is. Anyway, our x and y is there. Now, that distance there is now going to become the distance on the y. And that distance there for y is going to be the distance on x. So that point there ends up coming about there. A bit hard to draw. And this point here, okay, that distance there is going to be our x distance. And that distance there becomes our y. So we actually get the point somewhere over here. Okay, so that point goes over there, that point goes over there. So what we're basically doing on this point here, well, that's exactly the same distance on the y's as it is for x, because this line shows the midway point. So that point stays the same, but this point over here will come over here, because this distance here will become that distance there. That distance there will become that distance there. Alright, fair bit to take in, but let's draw it. So it's going to go through that point and go up. Ugh. Something like that. So essentially what we're doing is a reflection along the y equals x line. Okay, this is y equals x. And to find the inverse, we swap all the x values for the y values and all the y values for the x values. And so it's going to be a reflection along the y equals x graph, or line. Okay, so that point there becomes there, that point there goes there, that point there goes there. Same with that one, and that one. Alright, and it does that for every single point. So we get a reflection along that line there. So looking at this line, our new line, our inverse, what's the domain of that? Well, it's going to be from 0 to infinity, which is what our range was for our first one, because we swapped them for the x's and the y's. Okay, I know there's a lot to take in, and it is quite complicated to start with. And after a few examples, it might start to sink in a little bit. So that's the graphs of the inverse functions. Okay, we might do another example. So let's start with the equation y equals, let's go 3x. Well, first let's draw a set of axes. And this line here, 3x, okay, goes through the origin. It's quite steep. So that's that line there. Now, what happens for the inverse operation? Let's do it algebraically. So swap the x and y. So x equals 3y. So then y equals x on 3. Well, that's just the line. Let's go green. So graph that line, y equals x on 3. Well, that will be basically that line there. Okay, that's our inverse line. Now, as I said before, basically what we're doing is we're drawing the line. Oh, that's horrible. That goes, this blue line is going to be the y equals x line. Okay, so it goes midway between all those points, and then all these points on our original function gets reflected along that line. So as you can see, all those points there end up being reflected. So I'm running out of colours here. So that point there goes down to there. That point there goes down there. Okay, and that happens along the whole line. Yep. Okay, so can you see what we're kind of doing? If not, you can ask some questions in class. So our domain for that one is from 0, well, it's going to be all real numbers, as with our domain, our range, sorry. So we go all real numbers, okay, and it's going to be all real numbers for this one as well. So a little bit easier example than this one, but essentially does the same thing. So all the points get reflected along that line. Just one last thing, I think. So in notation for the inverse functions. So neither the original relation nor its inverse have to be functions. So just a bit of an important point there. However, when both a relation and its inverse are functions, there is a special symbol for the name of its inverse. Now, I had a quick little example of this before, which I didn't really point out. So if the inverse is a function, and we label that as f, then the inverse function is denoted by f minus 1. So as I said, similar to sine, cos and tan, how we write that minus 1, it's our inverse operation, or inverse function, which is f minus 1. So the equation of the inverse of the square root function can be written as inverse of x which is x squared. In mapping notation, alright, so f of x, we said, goes from 0 to infinity for our square root function. And that's part of the codomain of all real numbers. Then the inverse function is going to be 0 to infinity for x squared. So that's our domain. So the domain of f of, or our inverse function, equals the range of the f, and the range of the inverse equals the domain of f. So we can say the domain of the inverse is equal to the range of the function, and the range of the inverse is equal to the domain of the function. So let's have a look at this example here. So consider the linear function f of x equals 2x take 2. State the domain and determine the range. Well, we can draw that quite quickly. So 2x take 2. So we've got the 2x function, or 2x line, sorry, and it's been moved down 2. So it's going to go down somewhere like that. What's the domain of it? Well, it's just going to be all real numbers. So negative infinity to positive infinity. Determine the range of f. Well, that'll be the same thing. It's all real numbers. Except we've got 0 to 3. So we don't actually have all numbers. So let's get rid of that line. We actually start from 0 and go to 3. So where's 0? It's down here, and we go up to 3, which is about there. What happens at 3? What is that point? Well, this is minus 2. At 3, we'll have 2 times 3, which is 6. Take 2 is 4. So that'll be that point there, 3, 4. And it's not including that point. So our domain is going to be from 0 to 3, not including, but we do include that one. Now our range goes from minus 2 up to 4. So including 0, and it goes up to 4, not including. State the domain and the range of the inverse function. So if we go back to some definitions here, so the domain of f, the inverse, equals the range of the original function. So what did I say? The domain equals the range. So f, okay, so for our inverse, our domain is going to be the range, which is this one here. So 0 to 4. And the range of the inverse equals the domain of the function. So that's that one there. So that comes down there, and that comes down there. Okay, so we've done A, and that's B. Form the rule for the inverse and express the inverse function in mapping notation. Now let's go to a new page. So we've got y equals 2x take 2. Now to find the inverse, we have to interchange x and y. So x equals 2, y take 2. Now we add 2 and then we'll divide by 2. So x plus 2 divided by 2 is what our y is. Now I can simplify it a little bit by splitting up the fraction, which is x on 2, or half x, plus 1. Okay, so that's our function for the inverse. Form the rule for the inverse and express the inverse function in mapping notation. So in mapping notation, I actually say f of minus 1, our inverse, of x is equal to x over 2 plus 1. And now that's it. That's all we have to do. Part D is now sketch the graphs of f of x and f, our inverse. So I'm just going to copy this. And we said doesn't matter. the inverse is x on 2 plus 2, or plus 1, sorry, I think. X on 2 plus 1, yep. Now, how do we graph that? Well, we've got a straight line, and it's been, so x on 2 would look something like that, except we've pushed it up 1. So it'll go through the point 1. So it'll be quite flat, but something looks like that. Now, the other thing to remember is, actually that's not a very good one. The other thing to remember is what our domain is, so from 0 to 4, and our range goes from 0 to 3. So I should goes from 0 to 0 to 4. So it's about, yeah, not a very good diagram, but 0 to 4, and then from 3 to, sorry, 0 to 3, which is what we have. So 0 to 3, and 0 to 4. So it looks something like that. So let's have a look. So we got our function, domain from 0 to 3, endpoints, x equals 0, f of 0 equals minus 2. So that's that point there. That's for our original function. And when x equals 3, we have 4. So that was our other point up here, 3, 4. Our domain of our inverse is the range for the function. Now the range for the function goes from minus 2 to 4. So I've actually done a mistake here, because we actually go from minus 2 to 4. So let's just fix this up. I had the feeling something was wrong, and that's why. So minus 2, that should be. So that means our domain for the first one should be from minus 2 to 4. So minus 2 to 4. And our range for the inverse is the domain of the function, which is 0 to 3. So that was okay. All the rest should be fine. I'm just going to fix up our graph. So it goes from minus 2 to 4. So let's just start again. So we've got a set of axes. Now our original function went from minus 2 to 3. So that was 4 and that was 3. Now our range, our domain for our inverse is going to go from minus 2 up to 3. No, it should be 4, sorry. So it should go up to 4. Yeah, minus 2 to 4. Okay, so here's minus 2. Remember, this is for our domain. So minus 2. It goes up to 4 there. And what's the range? Well, that'll be from 0 all the way up to 3. So that's what we should get. Again, we can actually make it a little bit easier if we draw a line that goes through, and it should be very roughly like that. Okay, so as you can see, the intersection of the 3 points, so this is the line y equals x, and we've got the reflection. So this point here comes down there, that point there to there, etc. Alright, so that's inverse functions. So that was example 17. And as you can see here, a little bit better diagram than what I've drawn. So let's get a doesn't want to load. That's okay. Alright, so better example than what I'd drawn. Conditions for the inverse function to exist. The inverse of a parabola with equation y equals x squared can be obtained algebraically by interchanging x and y to give x equals y squared, which is the equation of its inverse. So on the side we can see in blue y equals x squared. In the purple, that's our x equals y squared, or y equals the plus or minus square root of x. Okay, we had a look at that in chapter 6.5, I think, looking at the y squared equals x graph. Alright, so for the inverse to exist, f must be a one-to-one function. Okay, so the reflection has interchanged the types of correspondence as well as the domains and ranges. The many-to-one function, so many going across to one function, y equals x squared, has an inverse with a one-to-many correspondence. Therefore, its inverse is not a function. This is important for implication for functions. Okay. Alright, let's just finish off this bit with a couple more examples. So, work example 18. Consider the quadratic function defined by y equals 2 take x squared. Form the rule for its inverse. First off, okay, we've got y equals 2 take x squared. The inverse is going to be interchange x and y, so x equals 2 take y squared, and then just solve for y. So take 2, divide by minus 1, or times by minus 1. Okay, becomes a negative equals y squared. Okay, already you should note that we're going to have a problem because when we square root both sides, we'll have the square root of negative x take 2, which equals y. okay, and it'll be plus and minus. Now, we've got x take 2 and then get the negative of it. So if we have x equals 4, 4 take 2 is 2, and it'll be negative 2. Square root of negative 2 doesn't exist. Okay, negative numbers. So minus 2 times, well, minus 2 take 2 is minus 4, negative. Okay, so we can have a possible solution for it, but in terms of explain why the inverse is not a function, if we go back to this one, for f, our inverse function, to exist, f must be a one-to-one function. 2 take x squared, here's my set of axes. 2 take x squared, well, it's going to be the x squared graph, and we've moved down twice at minus 2. No, sorry. So it's 2 take x squared, other way around. Undo that. 2 take x squared, we've got a negative graph, so it'll be something like that, okay, at positive 2. Now, why can't our inverse be a function? Okay, from the rule, our original function has to be a one-to-one correspondence. If we do our horizontal line, okay, we get a many to one. Okay, so because it's not a one-to-one function, our inverse isn't going to be a function. Okay, even though our original function is a function, okay, because we've got the vertical line test that passes, so it is a function, our inverse is not going to be a function. Alright, so sketch the graph of y equals 2 take x squared, for x is all negative numbers. Now let's just clear all that. Okay, y equals 2 take x squared, and we want all x is negative numbers. Well, it's just going to be all those numbers that I had there. That's not very good. Yep, so all those numbers. Okay, I got negative x on this side. It's going to be all those negative numbers. And use this to sketch its inverse. Okay, when you're drawing the graphs, it's the really easiest to draw in your reflection line, so y equals x, and then just do a reflection. So we've got a point there. Okay, as you can see, they all correspond along that reflection. Okay, so that's basically the inverse function sketch. So just draw your line and then just do a reflection along that line. Form the equation of the inverse. Well, what's the equation of that inverse? So if we've got y equals 2 take x squared, our inverse is going to be x equals 2 take y squared. Okay, now rearrange to find y by itself, so x take 2. Okay, get the negative of it and then get the square root of it. And it's going to be plus and minus. So that's our inverse, which we did down here anyway. So form the equation of the inverse, okay, for all negative numbers. So which numbers did we have? It'll be So down this way for our domain goes to negative infinity. What's this point here? Well, this point up here was positive 2 because we moved the graph up 2. This one's going to be positive 2 as well, okay, because it corresponds to that point. So it's going to be that for all numbers for x less than 2. Okay, so all those numbers less than 2. At what point do the two graphs intersect? Well, they intersect at this point down here. How do we solve that? Well, it's going to be simultaneous equations. So we've got y equals x squared plus 2. 2 take x squared. And we've also got this line here for our inverse function. So I could say, when does that intersect with y equals 2 take x squared? When do they both occur? Alright, so solving one with the other. But it will probably be easier if I find when they intersect with the reflection line, which is y equals x. Okay, so you've got a few different options. You can either solve when our original function equals the inverse function. You can solve when the original function equals our reflection line, or you can solve when the inverse function equals the reflection line. So I'm actually going to go when this is equal to our reflection line. So when that is equal to y equals x. So solving or substituting, we have x equals 2 take x squared. Okay, here's my first one. There's the second equation using simultaneous equations. 1 equals 2. So x equals 2, that's a 2 by the way, 2 take x squared. Solving for x, if I add x squared and then take 2, so I'll have x squared take, plus x, take 2 equals 0. Now I've got a quadratic, I can solve two numbers, multiply together to get minus 2. So it'll be positive 2 and minus 1. X take 1 equals 0. Okay, so either x equals minus 2 or x equals 1. Positive 1. So what that's saying is, if we go back, if I kept drawing that graph along here, and if I kept drawing that graph this way, we'd have 2 points where it intersects. One at the positive value, and one at the negative part. Okay, we're just interested in this point here. Okay, because we've got a restricted domain. So which one was it? We either had x equals minus 2 or x equals positive 1. Okay, we want this value here. So our solution is they intersect at x equals minus 2. So that's our solution for this one. At what point do the 2 points intersect? They intersect at x equals minus 2. Now you can check the examples there. Slightly different to what I've done, but they have the same answer. Okay, so x equals minus 2, x equals 1. We don't want positive 1 because we only want the negative numbers, so it intersects at minus 2, minus 2. Now I'm going to leave the video there. So next part is we just need to have a look at the x cubed graph and hybrid functions. Okay, thanks for watching.